All right, good morning, AP Calculus BC. It's good to see you online. This is a quick introductory video that turns into some notes for our first online lesson. So I'm going to switch it over to the PowerPoint and just follow along. All right, so just to kick us off, reminding us of our big goal here, we are still shooting for 30 out of 30 students to score a 4 or 5 on the AP Calculus BC test on May 5th, 2020 to earn college credit in Calculus 1 or 2 at our respective institutions. So with that, we're going to keep chasing this goal despite the coronavirus. We're going to find a way to make it happen. So here was our original game plan. Next week, we are going to do all AP review for the following week, which would be Q3 IA assessments. We currently don't have a plan right now for IAs for Q3, so we're going to have to put that on hold for a moment. We were then going to cover Polar before spring break, and then when we got back from spring break, cover these two quick topics, improper integrals and the integral test, followed by AP review. This would then take us directly into the AP Calculus BC test on May 5th. As many of you know already, for the next 3 weeks, we'll be doing remote instruction. So here's our new game plan. Today and tomorrow, we're going to focus on improper integrals. We'll also introduce the integral test, and we'll do some AP review later this week. Next week, we'll focus on polar coordinates, which has some connections to parametric coordinates. So we'll see some connections next week with that. Then AP review. Week after that, AP review. Then we'll have spring break. My understanding is there will be no classes during spring break. That was originally scheduled. Following that, the plan right now is to be back in school, and we will get back to some AP review. And then the test for AP Calculus BC will be on May 5th. I have not heard any changes from the College Board about this, so we're going to proceed with that, assuming that that's on May 5th. In terms of grading, here's a quick overview of the grading policy for my class, and it's also going to be very similar for your other classes. First, there's an attendance grade. This is going to be captured in PowerSchool as a classwork assignment. And this will be used for reporting attendance across the school. However, this does not affect your class grade. I'm going to check a box that says do not including final class grade, and that will not be counted in your A, B, C, D, or whatever grade you receive overall for the class. The following 2 grades will count towards your grade. Classwork grade entered in PowerSchool as a classwork assignment. And this is the completion of the classwork practice that I will walk you through and work with you on during class from 8:20 to 9 o'clock. And this needs to be uploaded to Google Classroom. Most of this will be on paper, so it will require you to scan it using Adobe Scan and upload it. This is due at 4 p.m. each day. Then there's a homework grade entered in PowerSchool as a homework assignment. This will be a daily exit ticket, which has a quick 1 or 2 questions about the topic of the day. And this needs to be submitted to Google Classroom. This is due by 4 p.m. each day as well. Here's a quick overall review of the lesson structure for our lessons. This may change based off how online lessons go to better accommodate your learning. So from 8 to 8:20, watch a 20-minute video independently. This will be me modeling some new skills, maybe reviewing some questions you had from the day before, and you'll take notes here when appropriate in notebook or loose leaf. From 8:20 to 9, I will be online to assist with classwork practice. We'll complete the classwork practice, submit that to Classroom, and then I'll try to leave at least 5 minutes to complete the exit ticket to submit to Classroom. All work for the day is due by 4 p.m. the same day. And so I have to enter these by 6 p.m. and Mr. Mann, Ms. Syed will be checking to make sure I've entered these. So I need your work by 4 p.m. that day. Thinking about grading for a moment, the submission of this classwork and that exit ticket as your homework grade, that is how it will determine your attendance. So based off the submission of those, that's how I'll determine your attendance. And I need to enter those 3 assignments by 6 p.m. each day. When I log on around 8:20 and see you on the Zoom chat, we'll have a chance to ask any clarifying questions about this. So if you have those, please write those down because we're going to get started with our first e-lesson in a moment. All right, so just like we do in class, title your notes, 1118, Improper Integrals, Part 1. and we're going to try out this online learning. So here we go. So starting with a recall slide, on the left, we have analyzed series like the one you see on the left. You should recognize that that's a geometric series. And for these series, we've determined if they converge or diverge, and we've also determined their sum through different techniques. In this case, the sum of this geometric series is 2. You can see the arithmetic there in the bottom left. Today, we're going to see integrals like the one you see on the right side of the screen. And integrals like these can converge or diverge too, just like series. So we'll make that connection today. Another important connection to make is to integrals like you see on the left. So we have the integral from 1 to 5, 1 over x squared dx. We've done this before. You simply take the antiderivative, substitute the limits of integration, and subtract using our evaluation theorem. However, we're going to see an integral like this one on the right, and we can borrow some of the same techniques we use for the integral on the left, but we'll need to figure out how to handle the infinity in the top of the integral there. So with that, here's example 1. Take a moment to copy that down. If you need to pause the video to do so, that's fine. And I had the chance to bring home a document camera from school, so I'm going to try that out and see how that shows. When we get to the in-person sessions, let me know how effective that is. All right, here we go. Just like class, here is the first example. So follow me carefully for how to solve this one. Estimate the following integral. Integral from 1 to infinity, 1 over x squared dx. All right, I need to somehow evaluate this integral. Well, I know from my prior knowledge that I could take the antiderivative of the inside and then plug in upper lower limits and subtract. Let's try taking just the antiderivative first. So I know I could re-look at this integral as 1 to infinity, x to the negative 2 dx, just like that. Then using my anti-power rule, I know that's going to become x to the negative 1 over negative 1. And then I'll carry my limits 1 to infinity like this. And then I can re-look at this by accounting for that new exponent of negative 1. And I can look at this as negative 1 over x evaluated from 1 to infinity. All right, same process so far. Let's figure out how we might handle this infinity. So I know I could plug 1 in, and that would be the part that I subtract later. What happens when I plug this infinity in? What happens when I plug this infinity in? Well, I can't really plug in infinity, but I can take a limit as some value goes to infinity. So what we can do is this equation here will be equivalent to the limit as t. I'm just going to choose any variable that I haven't seen yet. T approaches infinity of negative 1 over x evaluated from 1. Instead of infinity, I'm going to write t. So to address this infinity, I can rewrite the piece I have here. Limit as t goes to infinity, which corresponds to that upper limit. Now let's think about how this might work. We could have the limit as t goes to infinity of this. I know if t goes to infinity, this denominator is going to get very, very large. If that gets very, very large, then I know that the whole fraction would approach 0. So when I evaluate that limit, I would get 0 here. And then when I plug in 1, I don't even need to consider the limit because this is just 1. So 1 minus, when I plug in 1 here, that would be negative 1 over 1. So this integral comes out to be just 1. Before we go much further, let's make sure we have a visual of what's happening here. So here's my graph, y equals 1 over x squared. We know our lower limit was 1, and then our upper limit was infinity. So effectively, we have this area that keeps growing and growing and growing and growing. And based off the work we've done, we can see that this converges to 1. So it's a couple things. This integral converges. And second thing, the area converges to 1. Excellent there. I'll leave that there for a moment, nice and neat, so you can catch up. Feel free to pause the video if you need. All right, I'm gonna switch back to our PowerPoint. So we just completed this example, and now we're gonna move to some key definitions. These can feel pretty heavy, but they're pretty quick to use, and we actually already used one of them, so here they are. Three key parts here. So if we have some integral from a to t f of x dx exists for every t greater than a, then the integral from a to infinity f of x dx can be rewritten as limit as t approaches infinity from a to t f of x dx. This is just like we did in the example a moment ago, where we saw this infinity in the upper limit, and then we rewrote the integral as limit as t goes to infinity of integral from a to t f of x dx. And this will be true as long as that limit exists and is finite. All right, I just found an annotation tool. This will be more helpful as we look to this next one. Quick typo here. Quick typo here, let's make this if this upper limit of b, and then this lower limit, make this a t. And then for every t less than b, then we have the following statement. Let's read through that together. If, I change my color, here we go. So if this integral exists, integral from t to b, f of x dx exists for every t less than b, then we can rewrite the integral from negative infinity to b, f of x dx as the limit as t approaches, that should say negative infinity of t to b, f of x dx, provided the limit exists and is finite. Very similar principle to what we saw up in here in the top, although now the infinity is in the lower limit. So that covers 2 and covers 1. Let's take a look at statement number 3. If we have a integral from infinity to c f of x dx and c to infinity f of x dx are both convergent, then if we have an integral with an infinity in the lower limit and the upper limit, we can break apart that integral into 2 integrals with some common endpoint c. We'll see an example like this in example 3, because this seems a little bit different than what we've seen before. And as long as these 2 integrals exist, as per the definitions up here at 1 and 2, then we know that the original integral from negative infinity to infinity f of x dx will also exist. That covers those 3 key definitions. If you need more time to copy those down, pause the video, and we'll pick up in a second. All right, here's example 2. Let me get rid of all these markings, clear all drawings. Great. Determine if the following integral is convergent or divergent. If it's convergent, find its value. So I'm going to flip back to paper so we can tackle this one. Here we go, example 2. Take a moment to copy that down if you have not already. And let's get started. So just like I did in the previous one, I'm going to take the antiderivative of my integrand here. We know that's natural log absolute value of x, evaluated from 1 to infinity. And then to handle that infinity, we can rewrite that as limit as t goes to infinity of ln of x from 1, keeping that finite limit, but then changing this upper limit to t. Then when I evaluate this, we know this will become, if I take the limit as t goes to infinity of t, that's going to make that argument t go to infinity, which would make ln of t go to infinity as well. So this ends up being infinity minus, then when we plug that 1 in, we would get infinity minus 1, which is effectively infinity. So when we get that infinity like this, we would determine the integral diverges. This is not a finite number, so this integral then diverges. Let's think about what's happening here graphically. So our graph here looks very similar to the previous one. However, this is 1 over x, and what we just showed is that this area keeps growing to infinity. So we might make a note here, keeps growing. So this integral, or this area, keeps growing and therefore diverges. It does not approach a finite number. It keeps growing unbounded. Yeah, that note, keeps growing unbounded. So we can say that that integral diverges. We can't find its sum because it diverges. All right, on to example number 3. See you in a minute. All right, before we get to example 3, quick key idea. This should look very familiar. Here's my annotation pen. Here we go. If a is greater than 0, so if this number here is greater than 0, then this integral is convergent if p is greater than 1 and divergent if p is less than or equal to 1. This should really click and make sense and seem similar to the p series test. Great. So this, we can apply the p-series test, or this is very similar to the p-series test because of this criteria. So this is not brand new. This connects directly to what we've learned about p-series. Now, let's clear those annotations, clear all drawings, and let's get to the next example. Example 3. See you on the paper version. All right, just finished example 2. Here is example 3. Determine if the following integral is convergent or divergent. If it's convergent, find its value. Same prompt, different integral. So in this case, I see I have an infinity in the upper limit and the lower limit. So using that third statement in your notes, we can break this into 2 integrals. I'm going to think about what value might I choose that's between negative infinity and infinity. In this case, I'm going to go with 1, or I go with 0 actually. So we're going to break this integral into negative infinity to 0, x e to the negative x squared dx, plus the integral from 0 to infinity, x e to the x negative x squared dx. So I've broken this into 2 integrals like this using that third statement that we saw earlier in our notes. And now I need to figure out how to find the antiderivative of these functions. These look pretty complex, but you have the skills to do this. So if I examine these, I see I have an inside function with its derivative hanging around. That is key to reveal that I will use U substitution in this case. So let's break that down. U will equal negative x squared. Du will equal negative 2x dx. We can then isolate for the x dx, du over negative 2 equals x dx, just like this. And then if I took the indefinite integral of e to the u times du over negative 2, that would be negative 1/2 e to the u plus c. And then I can substitute my u back in. This would equal negative 1/2 e to the negative x squared plus c. And so that was my work to find my antiderivative. Now let's come back to these improper integrals. So this first one, when we apply that antiderivative rule, negative 1/2 e to the negative x squared from negative infinity to 0 plus negative 1/2 e to the negative x squared from 0 to infinity. And now we just proceed using statements 1 and 2. So I could rewrite this one as limit as t goes to negative infinity of negative 1/2 e to the negative x squared t to 0 plus limit as t goes to negative infinity of negative 1/t e to the negative x squared all over from 0 to this t. So if I look at these two, I'm just going to apply that same thinking from before. If t approaches negative infinity, first we'll look at this upper limit actually. When I plug in 0 here, I would get e to the 0, which is 1 times negative 1/2. So I'm going to put negative 1/2 in front like this. And then e to the 0, we got negative 1/2 here. And then when t approaches negative infinity, that's going to make this negative infinity positive because it's going to be squared. But then the negative is going to make this be e to the negative infinity. And if I approach e to the x to the negative infinity direction, if I think about that, that is going to be approaching 0. So I'm going to subtract 0 and write that like this. Then we consider the next part. As t goes to positive infinity in this case, quick switch there. As t goes to positive infinity, this is going to approach negative infinity as well. So that will also be 0. And we're going to subtract. When I plug in 0 here, we saw that was negative 1/2. So that ended up being negative 1/2 plus 1/2, which equals 0. So this integral comes out to be 0. Huh, interesting. Let's take a peek on Desmos to see why that might be the case. All right, coming to Desmos, y equals x, e raised to the negative x raised to the 2. Ah, interesting. If we look at our graph here, we had negative 1/2 over here on the left. Let's get the annotation pen out. We had negative 1/2 over here. And we had positive 1/2 over here that we saw in our notes. So if we add negative 1/2 plus 1/2, we get 0. Makes sense because this area and this area will cancel out. With that, definitely tough content to master. So we'll dive into it together for the next 40 minutes. And I'll see you in a moment.